All right, let's get right into it. Today, we're going to pull back the curtain on one of the most important tools in any programmer's toolkit. We're not just going to talk about what a hash map is, we're actually going to build one completely from scratch. You know, you've probably used one 1,000 times. Anytime you need a super fast way to look something up, like finding a user by their ID, you reach for a hash map or a dictionary. It works so fast, it kind of feels like magic, right? Well, today, we're going to learn the trick. So here's our challenge, and it's a classic one. We have to design a fully working hash map from the ground up. That means no help from built-in libraries, no shortcuts. We have to build the entire engine ourselves.
Now, for our hash map to be, a hash map, it needs to do three basic things, and it needs to do them well. We need a way to put a key value pair in, a way to get a value back out using a key, and a way to remove a pair. These three are the absolute heart of any key value store.
Okay, so where do we even begin? Well, when you're starting out, the most obvious idea is usually the simplest one. So let's follow that first instinct and just see where it takes us. The problem says our keys are going to be numbers, all the way from 0 up to 1,000,000. So what's the most direct way to store that? How about we just make a giant array and use the key itself as the index? You want to store something for key 123? Just stick it in index 123. Seems easy enough. And here's where that simple idea hits a massive wall. To handle a key of 1,000,000, our array needs 1,000,001 slots. But, and this is the key, the problem also says we're only going to perform at most 10,000 operations. So we'd be setting aside 1,000,000 spots in memory just to store maybe a few thousand items? That's not just inefficient, it's a colossal waste of space. So this is the classic trade-off, right? The giant array gives us lightning fast, O1 access. That means getting a value is instantaneous, but the cost is that insane memory waste. What we really want is the best of both worlds, that speed, but without reserving 1,000,000 empty chairs for a party with only a few guests.
And that brings us to the really elegant solution. It's a fantastic technique called separate chaining, and it's exactly how we're going to solve our big space problem.
Okay, here's the big idea. Instead of one massive array, we're going to use a much smaller one. We'll call each slot in this array a bucket. Then we need a way to turn our big key, like, say, 950,000, into a small index that actually fits in our small array. Now, what if two different keys point to the same bucket? We call that a collision, and it's no big deal. We just store them both in a simple list inside that one bucket.
So the whole process breaks down into 3 simple steps, every single time. First, you hash the key, which is just a fancy way of saying you run it through a quick calculation to get your bucket index. Second, you go to that bucket. And third, you just deal with a short little list you find inside. So, how big should our small array be? Well, here's a bit of secret sauce from computer science. To make sure our keys spread out nice and evenly across the buckets and we don't get too many collisions, it's a really good practice to make the array size a prime number. For what we're doing, a number like 1009 is pretty much perfect.
Okay, so we've got our blueprint, an array of lists. Let's get our hands dirty now and see exactly how our put, get, and remove functions are going to work with this structure. First up, put. When we want to add a new item or maybe update an old one, the plan is straightforward. Find the right bucket, then check the list inside. If our key is already there, we update it. If not, we add it. So let's walk through it. We hash the key, maybe something simple like key modulus 1009, to get our bucket index. We jump right to that list. Then we do a quick scan of the items in it. Is our key here? If it is, great. We just overwrite the old value with the new one. And if we get to the end of the list and don't find it, we just tack our new key value pair on the end. Simple as that.
All right, now for get. How do we retrieve a value? You're probably seeing the pattern already. The logic is almost identical, but instead of writing data, we're just reading it.
Once again, we hash the key, we find the index, we go to the bucket, we scan that little list, checking each key. If we find a match, bingo, we return the value that goes with it. If we search the whole list and come up empty, it means the key isn't in our map, so we just return -1, exactly like the problem asks.
And finally, our remove function. I bet you can guess exactly how this is going to work. We find the bucket, we look for the key, and if we find it, we just take it out.
It's the same dance one last time. Hash the key to get the index, go to the right bucket, and scan the list. As soon as we find the item with our key, we simply pluck it out of the list. And if the key wasn't there in the first place, no big deal. We just do nothing. The operation is over.
So we've gone through all the nuts and bolts. Now let's just zoom out for a second and appreciate why this design is so incredibly powerful and used all over the place.
This right here, This is the real payoff. On average, our operations are O of 1, or constant time. That's a fancy way of saying they're basically instantaneous. Why? Because our prime number hashing spreads the keys out so well that the lists inside our bucket stay incredibly short. Now, is there a nightmare worst-case scenario where every key lands in the same bucket? Sure, but it's so statistically rare with a good hash that we can count on that amazing average case speed.
And check out how tough this design is. It handles all the weird little edge cases perfectly. A key of 0? No problem. Collisions? That's literally what the lists are designed for. Updating a key is built right into the put logic. Trying to get or remove something that doesn't exist? It handles it gracefully without breaking a sweat. It's just a really robust and elegant solution.
And there you have it. We took a simple array, some simple lists, and a clever idea about hashing, and we combined them to build a memory-efficient, incredibly fast hash map from the ground up. We've taken the magic and turned it into clear, simple logic.
But that does leave us with one last really interesting question to think about. Our design works perfectly for this problem because it has a fixed size. But what happens in a real-world application, where you might keep adding millions and millions of items? What happens when our buckets start to get crowded and those short lists turn into long ones, slowing everything down? Well, solving that problem, that's where things get even more interesting. And that's a story for another time.